Hello and welcome back to Calculus 1. We are starting chapter 5 on integration. But before we do any integrals and any calculus, we have the first section which will do some middle school stuff. We are going to approximate area under the curve. We're going to multiply and add some numbers and be done with this section. It's very basic. We're also going to introduce summation notation in this one and then use it to calculate area under the curve long way, and you'll see what that means. So now we are going to take a look at approximating area under the curve. Now if your curve is a straight line, let's say y equals to 3, then you can have a simple rectangle under that curve, and we have the formula for that rectangle, for area of the rectangle. So if I have, let's say, y equals 3, that's not a 3, that's a 3, on x and y coordinate system, and say you go from 2 to whatever the hell this is, 3, 4, 5, 6, 7, 8, there we go. You have the area in here, which is a rectangle, and you can just use the rectangle formula of length times the width. So you have 8 minus 2 times 3 for 18. Area is 18. Can you use calculus for this? Yeah, but we cannot just use the formula. Similarly, if you have a linear line at an angle that will cut through, let's say over here, 3 and 1, 2, 3, 4, 5, 6, then you have a triangle, and you can calculate that this is 3, this is 6, so you can compute your area as 1/2 base times the height and get your area of 9. So when you have circle, you have some of these shapes that you know, right? It's not a big deal to calculate area because you know the formulas. But what happens if you have a curve? Let's say you have x squared, you have square root of x, you have ln x, you have e to the x, right? All of these sine, cosine, right? They all curve. How do you find area under those? Because they're not going to fit any of the formulas, you know, right? So now what we are going to do, when we can't use basic geometry, we can approximate area under the curve by creating the vertical stripes and then computing areas of those. And that will give us approximation for our... So let's put, usually I use square root of x. And what I'm going to do is I'm going to put, let's say, 5 of these. So this is my square root of x, that's the x, that's the y. And I'm going to use left hand approximation in this case. Now, left hand approximation means we use left point to create rectangle. Now you're going to say, what left point? Well, if you take a look at any of these, it has a left point and a right point. You use the left point to create a rectangle. Left point to create a rectangle. Left point to create a rectangle. Another left, and over here the left is at 0, so you actually don't have a rectangle at all. Now, you see there's a lot of error, right? Everything that I color in this pink is error. So your approximated area here is less than the actual area because all of this pink, right, colored areas are actually areas of error. But you know what? It's better than nothing. So you will just, live with that. Now, the way I structure this, as I said, 0, 1, 2, 3, 4, and 5, which makes these points square root of 0, square root of 1, square root of 2, square root of 3, square root of 4. Note that I'm not using square root of 5 because that would not be a left point for anything, because there is nothing to the right of 5, right? There's nothing to the right of 5, so 5 can't be the left point of something that it's not to its right. Now you're gonna rewind this and listen to it, and again, to make sure that you get that. All right, so now, what do I have for my rectangles? Rectangle 1, rectangle 2, rectangle 3, 4, and 5. Well, I have area 1 is going to be, the length is 1 times square root of 0, area is 0. Area 2, again, width is 1 times square root of 1, we get 1. Area 3 is 1 times square root of 2, which is about 1.4. You can put 17 decimals if you want, doesn't matter. A4, the fourth rectangle, is going to be 1 times square root of 3. Guys, if I isolate fourth rectangle here, you observe that its height is at root 3, because I computed the function at 3. My function is square root of x. So if x is 3, then the height would be at root 3. And then the final rectangle here, which be rectangle 5, area of the fifth rectangle is 1 times root 4. Oops, I didn't compute this one at 1.7 and this one at 2. So now I add them all for the approximated area under the curve 2, 3, 4, 5, 6.1. Now, I know that this is not the actual area, but it's at least close, right? So I know that my true area should be larger than 6.1, because there is a lot of that pink that we actually didn't count because rectangles didn't catch it. But we know it's, maybe true area is somewhere around, let's say, 7 or something. So that's when you use left approximation, meaning for each rectangle, you are using the left point touching the curve, and then you are calculating the function value for the height of each rectangle at those values, right, where you went to the left. Now, the next part is to do the same problem, but now use right-hand approximation. We're going to use the right points, and you'll see that everything shifts a little bit to the right. So here I have my square root of x, and I'm still going to draw the same 5 rectangles. And now we are going to use right-hand approximation, meaning that my values from before 0, 1, 2, 3, 4, 5 are going to use for each rectangle right point. So now we're going to draw rectangles to the right. Gotta extend from right, go left, down, from right, go left, down, from right, go left, down. Now we see that we have, in this particular case, more area than we need, right? And because we have more area, this calculation is going to overshoot the area, which means that the true area is going to be in between the two numbers, right? Now, what are the values I'm using? Well, this time I'm using square root of 1, square root of 2, square root of 3, square root of 4, and square root of 5 for my calculations. Rectangle 1, rectangle 2, rectangle 3, all the way up to 5. Area 1 is, the width is 1, because it's between 0 and 1, so it's 1, times square root of 1 is 1. Area 2 is 1 times root 2, which is 1.4. Area 3 is 1 times root 3, which is 1.7. About. Area 4 is exactly 2. And area 5, the fifth rectangle, 1 times root 5, is about 2.2. So now when you add them all, you get that the area is approximated by 2, 4, 6, 7, 8.3, right? 6, 7, 8, 3. So 8.3. True area is somewhere in between 6.1 and 8.3. We don't know exactly where, we just know it's in between. Can you run the average and claim it's 7.2? Yeah, it's going to be close. Is it 7.2? No, it's not. So we know that area is in this range. We don't know exactly where. And we want to improve on this. How do you improve on this?
Change the shape?
Well, the shape is square root of x. We can't change the function.
No, instead of drawing a box, maybe a different shape.
Oh, that's Calc 2. Okay. Haha. So, yes, in Calc 2, you're going to use trapezoid and Simpson rule, and then graduate school, cubic splines, and all this kind of stuff. But in this case, we keep the shape. We're just going to add a lot more of them. All right? Look what happens if I split each one of these in half. So I'm going to draw the same image as before. So I have my square root of x, and then I'm going to draw these again 1 through 5. So 0, 1, 2, 3, 4. Very good, 5. All right. So now let's use right approximation again. So you go to the right, go to the left actually, right, go to the left, right, go to the left, right, go to the left. Good. Now we see how much error we have. But let's say that you draw twice as many of these rectangles. So that means that through the middle of each one of these, you're going to have that. And there we go. And now if you draw those rectangles to the right, you will see that they will chop the error. And I hope you see that the new error is this much and this much and this much and this much, right? And you see that you eliminated all of these red X's here. That's the error that you eliminated because you used thinner rectangles. This tells you that if you use infinitely many, infinitely thin rectangles, you will actually have the exact answer, right? Now, calculating infinitely many thin rectangles is not a fun thing to do, but in computer application, put in 10,000. Obviously, those of you who are computer science majors will be coding this tonight, because why not, right? Some of you will be coding this tonight that still have functional computers. So it's a very simple thing to code, right? And you can ask for the user input of how many rectangles do you want to use. Obviously using on exam 4 or 5 rectangles that you can compute by hand like this, but the computer can compute 10,000 rectangles like this. So you might want to have a code for that. So this picture here shows that adding more rectangles reduces error. So it's a trade-off game, right? More calculations, less error, less calculations, more error, right? So you can't have both ways. So you make the decision of how many rectangles you're going to do, and the more you put, obviously, the better approximation you have, because every time you introduce more rectangles, the amount of error will go down. The question is, how much error can you actually have, because nothing is precise in engineering, and you have the safety factor to multiply by and a whole bunch of stuff, right? So there could be a lot of error in some of these. All right, cool. So now we understand the left sum and the right sum, and let's talk about actually getting these in a theoretical setting. Right, so now here is a theoretical setting for this, so we understand, and later on understand the notation. So I'm going to put some arbitrary function, f of x, and I am going to create arbitrary amount of these rectangles. The rectangles are always between your A and B, which is the interval on which you are considering the calculation. So AB is the need more space in between. Don't write this close to the graph. AB is closed interval. So that was earlier for us 0 to 5. And now I just have any arbitrary. Now we have x0 to be the first point, and then x1, x2, x3. The last one is xn, the one before is xn minus 1, and so on, which gives us rectangle number 1, rectangle number 2, rectangle number 3, and rectangle number n at the end. Now, depending whether you are using left or right sums, you are going to calculate f of x0, f of x1, f of x2, because that gives you heights, f of x3, and f of xn minus 1, f of xn as the last point there. I'm just going to have this as f of x. Good. So now, the difference that you have here for these splits is obviously labeled as delta x, because we said that delta x is a change in x. So when you go from x1 to x2, x2 to x3, x3 to x4, that's just change in x. So we call that delta x. Now, if you want to calculate the value for delta x is going to be b minus a divided by n, because that will give you delta x equals b minus a divided by n will give you the value for delta x. See, your partition doesn't have to be 0, 1, 2, 3, 4. You can have literally anything. Anything. So let's say your partition is on interval, let's say 3 to 8, and you have 6 rectangles. You'll have to shovel fractions in this case, because they're not going to land on integers. You calculate your delta x, and your delta x is 8 minus 3 divided by 6, which gives you 5 over 6. Fair? Now, your delta x is 5 over 6. You don't have to draw the whole thing. You can just draw the number line, which starts at 3, And since you're going to have 6 rectangles, you just make these divisions, and then you will start adding in fractions. So this is your x0. Your x1 is you add 5/6 to 3. Now, 3 is equal to 18/6, right? Because 18 divided by 6 is 3. And that's your 18/6 on the first one. So now you add 5. 18 plus 5 is very good. Now you add another 5. That's 28 over 6. 33 over 6. 38 over 6. 43 over 6. And then 48 over 6. Hold on. 48 over 6? How much is 48 over 6? You landed exactly at 8, right? So, yeah, I'm just going to ignore it. So, you have to land into B if you did all of the calculations correctly. Do I have 6 rectangles in between? Sure I do. 1, 2, 3, 4, 5, and 6. I have 6 rectangles, and I now know their x values. So the heights now are going to be f of 3, f of 23 over 6, f of 28 over 6. I know it's annoying, but again, we're not doing any calculus. We are calculating arithmetic here. So once we know these values are input x values for f of x0, f of x1, f of x2, to calculate all of the heights. Now that we have the delta x, we know that the first rectangle is delta x, which is the width, times f of x0 if you are using, let me do this. I'm going to switch this into red because we color coded earlier as red for, come on. Really? There we go. So we can have left over here. And then A2 is delta x times f of x1. A3 is delta x times fx2. And you can see them all because you know that your left hand approximation means you're using the left points for each one of the rectangles. You are always using the left point. Now, what you can conclude from here is that area is approximated by, you can factor out delta x, and you just have this f of x0 plus f of x1 plus f of x2 plus ... forever plus f of xn minus 1. You don't know what the last one is if you go all the way out, but you know that you are not using xn. Why are you not using xn? Because to create a left rectangle, the red one, that's it. That's the last one. And the height of that rectangle is computed at the point which is the last point minus delta x. Now, if you want to use the blue ones, then you are using the right side. In this case, you are not using A, you will be using B. So for the right side, your A1 is equal to delta x, which is the width, times f of x1. A2 is delta x times f of x2. A3 is delta x times f of x3. And on and on and on, giving you area is now delta x of f of x1 plus f of x2 plus f of x3 plus ... plus f of xn. So when you look at left and right approximation, they're using the same idea, except one is left is using the A, which is beginning of the interval, and the right is not using A, using B. Only the endpoints are different, but the middle looks the same, right? Because you see them, right? They're all the same in the middle. So now, what we do in mathematics, computer science, and so on, is we introduce notation with index to keep track of 0, 1, 2, 3, 4, 5, so we don't have to write all of this stuff. So we have xi to be the set of x0, x1, x2, x3, x4, dot, 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 forever. So I is the counter which has values 0, 1, 2, 3, 4, going on forever. So those are all sets. Now this is very useful because I really don't want to write all of the stuff out, right? I just want to write when I have f of xi, I have a set of f of x0, f of x1, f of x2, and going on forever. So this I is just the counter, and when you go to the next term or next member of the set, you just change that counter from 0 to 1, from 1 to 2, from 2 to 3. It's just counting 0, 1, 2, 3, 4, 5. So this is all ordered using, it's going to be called sequence in Calc 2, but we'll get there. All right, so the last part that we want to write here is the summation notation, so that we can further compress this into one short formula. So sum. So summation, where let's say I goes from 0 to 6 of I is going to be 0, plus 1, plus 2, plus 3, plus 4, plus 5, and stop at 6, because you have your input value where you start counting for i's, and then you have your terminal 6, which is on top of the sum, and that's when you're supposed to stop. Now you can add these values, right? Get 21. And the faster way of not writing this, we can use the summation. Now imagine if there were 100 numbers, right? And you sit and you write all 100, which would take a while. You can do it in 2 minutes, but you know. So when you learn the summation notation, it's used to compress this repeated addition, right, that it's ordered into a single formula. Now this formula here could be anything that it's based on I. You can change i's to n's or something else, but so let's say you have summation I starts, let's say, at 2 and goes to 5 because I'm lazy. And let's say you have I squared minus 2. Well, your I starts at 2. So you have 2 squared minus 2. And that's your first term. Plus 3 squared minus 2. Plus 4 squared minus 2. Plus 5 squared minus 2. So you can see that this I goes through all integer values in between the two numbers that you are given on the sum. You just cycle through all of them, and now you compute. 4 minus 2 is 2, 9 minus 2 is 7, 16 minus 2 is 14, and 25 minus 2 is 23. So that's 30, 46. So summation notation allows us to write these things in compact form. And now, if I have a summation of f of xi, where I starts to 0 and ends with some value n, let's first end it with 3. This means f of x0 plus f of x1 plus f of x2 plus f of x3, and I have to stop because I reached the integer. So this time I'm not computing with I is just the index that we use, and now you know what x0, what x1 and x2 because you worked out your delta x partitioning, right? So you know what to plug in. So now, what is my formula for the approximating area under the curve? The formula is delta x times summation of f of xi when it starts I equals 0 and goes, in this case, to n minus 1, and that is for the left-hand side. Why is the left-hand side? Because I'm using x0 and I'm ending with xn minus 1. That's the left-hand side. For the right-hand side, we have area is approximately equal to delta x times summation. I goes from 1 to n this time, and then we have f of xi, and these are the right sums. You can always draw representative rectangle here if it bothers you, and you know this is x0 and you know this is x1, so clearly, right, the first value that you have to have here is x0 because that's for the left rectangles, right? You create a rectangle using the left side, so the left side is above x0, so you are using x0 in your calculation times delta x, right? And then you go all the way. When you get to the last one with the xn, well, the left one is xn minus 1, which is why we have n minus 1 on top, right? So if you have 17 rectangles, then the top up there would be going to 16 because you used 0. So 16 digits and a 0 is 17. Calculations for 17 rectangles. If you're using the right-hand sums, right, then you're starting with x1 because when you go up from x1, you create a rectangle so that x1 can be the right point of that rectangle. So we're starting at 1, and again, on the tail end where n is, this would be xn, this would be xn minus 1, but you're using right triangles, rectangles, therefore you will be using xn this time. And that's it. More rectangles you pack in, you will have to deal with more calculations, but your result is going to be better. So no matter what the function is, you can always compute the values inside that function and then multiply everything by delta x and just be done. So let's take a look at one example where you can approximate area under the curve. So we can do that for, say, approximate area under the curve f of x equals 1 over 1 plus x. on the interval 0 to 4 using 6 rectangles. Now, what I want to assign is this side of the classroom, right? Left-hand sums. That side of the classroom, right-hand sums. So you guys are right sums, and those guys are left sums. Let's go. So the left sums, this side will be using a 0. That side will not be using 0. You guys are using 4, but these guys are not using 4. You'll figure it out when you draw the partition.
feel like I has to be 2/3, right? I feel like that's not right because
Let's take a look. We'll start with the left. So that's going to be in red. Well, actually, I just need, hold on. The partition is going to be the same for both. I start with delta x, which is 4 minus 0 divided by 6 to get 2/3. So delta x is 2/3. And then I will make 6 partition, right, with 6. 1, 2, 3, 4, 5, 6. This is x0, x1, x2, x3, x4, x5, and then x6, where the first a and the b are 0, 2/3, 4/3, 6/3, 8/3, 12/3, and 14. Something is wrong.
Yeah, 10/3. It should be 10/3 and then 12/3.
Yes, thank you. 10/3 and then 12/3. Good. Now, we know that we can simplify 6/3 is 2, right? And 12/3 is 4. So we know this is 4, which is our B. So that's great. Partitions worked well. And now for the left sum, I have area is approximated by delta x sum of f of x i's, where I starts at 0 and goes to 5, because it's n minus 1 for the left. So I have delta x, which is 2/3, times f of x0 plus f of x1 plus f of x2 plus f of x3 plus f of x4. Who did this? Plus f of x5. I could have done like 2 rectangles and be done by now. I give up. Let's go home. There we go. So that's 2/3. And now I have f of x0. Well, my function is 1 over 1 plus x. So that's 1 over 1 plus 0 plus 1 over 1 plus 1. No, lies. 2/3. There we go. 1 over 1 plus 4/3. 1 over 1 plus 6/3. Plus 1 over 1 plus 8/3. Plus 1 over 1 plus 10/3. And all of this is going to equal to a number. Yeah, do quick computing. Now the right is going to have the same similar. Delta x for them starts at 1 and ends with 6 f of xi's. So pretty much the same deal. 2/3. And now the first one is f of x1 plus f of x2 plus f of x3 plus f of x4 plus f of x5 plus f of x6, which is 2/3. I get to recycle all of this and just add the last one in, right? So it's not that big deal. So it's 1 over 1 plus 2/3 plus 1 over 1 plus 4/3 plus 1 over 1 plus last number is 4 equals to a different number. And now your true area will be in between the two numbers. Now I don't know which one is bigger, which one is smaller, right? That depends whether the function is increasing or decreasing. So I don't know which one goes where, but we'll put area, no, not area 1. Well, this is 1 over x. 0 to 4 should be decreasing. So if it's decreasing, then
left-hand side should have a
bigger number, yeah. So then number should go here, and a different number should go on the left. Or maybe they're switched. I don't know. Yeah, you will compute this if you care. Is this something that we compute this on a test for 4 rectangles just to show off the man's skills. But as I said, today's day and age, you write a simple 3 lines of code, right? And you just say for I equals 10,000, right? Let the loop add all of those values in, right? So there is a 3-line code that will calculate your dx, delta x, and store that. And you can definitely call it delta x as a variable, right? And then you need another variable. Then you'll need probably either array or something to store all of it, or you can compute delta x on the fly because you can just keep adding. There are many ways in which you can deal with this with the programming and be done. The trick is always to find the most compact way to write the code because that code works the fastest. That's the trick, right? Optimizing means use the smallest possible amount of calculations to get to a place because that's how you make your software faster. That's it. You plug those numbers in a calculator if you, I mean, it's not that. This is this is going to be over here 5/3, so it's 3/5 when you flip it. So it's easy to compute all of them. Then you need a common denominator, right? You can do it without a calculator. You are forced to do it without a calculator when you take this at Rutgers and NGIT. There's no calculator in any of their courses ever, right? So you sit to, on the exam, just grind through all of this without a calculator. There you go. Bye.